Hello, everyone. My name is Shante Hicks, and I'm going to do a presentation on the security features of Android versus iOS. So for an overview of topics, I'm going to start off by discussing the mobile operating system architecture for both Android and iOS. Then I will discuss the different security features that both operating systems use and compare them and contrast them. And in conclusion, I will discuss, based on these features, what is the better operating system in terms of security and how to better protect your information on your device, such as your phone or your tablet. The mobile operating system architecture is the first thing I'm going to discuss. And here, Android is a mobile mobile platform that is open source and based on Linux. And iOS is a mobile platform based on OS X used by iPhone and iPad devices exclusively. Each architecture is organized in layers that buffer the communications between the applications and the hardware. The abstraction layers for both Android and iOS provide a basis for the main security features that will be discussed in the following slides. There are 5 abstraction layers that buffer the communications between the applications and the hardware. The abstraction layers are Linux kernel, libraries, Android runtime, application framework, and applications. The Linux kernel is the base layer between the hardware and the application. It provides features for security, process memory, and device management, as well as hardware drivers. The libraries layer contains the open source software components to access database, create user interfaces, and provide graphics. Android runtime layer contains the Dalvik VM and core libraries. This layer is responsible for executing the application using Java-based technologies. Application framework provides the Java classes that provide high-level services to the Android apps. And the application contains the application layer contains all of the native and third-party Android applications. So iOS has 4 abstraction layers, which are core OS layer, core services layer, media layer, and Cocoa Touch layer. The core OS layer is the base layer of the iOS stack, and it interfaces directly with the mobile device hardware. This layer provides services such as low-level networking, access to external accessories, and operating system services such as memory management, file system handling, and process threads. The iOS core services layer provides the abstraction over the services provided in the core OS layer. It contains frameworks for interfacing with Apple-specific services such as Addressbook, iCloud, and App Store. The media layer contains the graphics, audio, and video technology geared towards creating and viewing multimedia on a mobile device. The Cocoa Touch layer serves as the key structure for constructing iOS applications. It provides the fundamental application infrastructure and key technologies such as multitasking, touch-based input, push notification, and many high-level system services. This layer provides a high layer system services that enable applications to actually interface with the device. So now we're going to go into the mobile security features and compare them. We're going to start off with permissions, and mobile application permissions basically govern what the app is allowed to do and access. Each platform has its own permissions protocol for granting access information like contacts, social media files, or accessing hardware like the camera or microphone. Smartphones with Android operating systems have their own security framework and are Linux-based. If we compare the desktop operating system where the same user ID is used to run various applications, apps running on Android are individually separated from one another and are run under distinct user IDs with individual processes. Each of the processors are given a distinct set of permissions to provide access to different resources of the smartphone. It is left to the programmer to give the required permissions in the Android app. Under different user IDs, the apps cannot read or write to other apps' data. The core mechanism of security in Android is based on these permissions for restricting the access of various core services. In Android, the app can be accessed downloaded from the Google Market or any other Play stores on the web. During the installation, the user is asked to accept a list of mandatory permissions in order to successfully install the app. The Android security framework prompts the users to accept the list of mandatory permissions during the installation process. There are major drawbacks to this, however. A malicious app may ask you for out-of-context permission to access critical data and the user is left with no choice than to follow the permissions that are dictated by the application. For a regular user, it's difficult to understand the appropriateness of the permissions of the app they want to install. In some cases, a novice user cannot understand if the permission is legitimate or not. As the permissions are left to the programmer's own understanding, the functionality of the app can be achieved with fewer number of permissions. For Apple, the Apple smartphones with iOS are not dependent on the users for their permissions when installing the app. Basic permissions come with each app, but certain permissions are requested when the app is being used. This allows for more granularity with regards to containing permissions within each app. So next we're going to talk about sandboxing. Application sandboxing, also called application containerization, is an approach to software development and mobile application management that limits the environment in which certain code can execute. The goal of sandboxing is to improve security by isolating an application to prevent outside malware intruders, system resources, or other applications from interacting with the protected app. The process of application sandboxing needs declarative permissions or entitlements. When a mobile app is created, the permissions or entitlements are signed and will not be dynamically changed at runtime by the mobile app or the mobile operating system. This determines the resources that can be shared, and those limits will never be extended beyond the definite declaration set at startup of the app. Sandboxing will assign a unique ID for each application and run it as a separate process that is isolated from the other applications. Sandboxing for Apple, iOS enforces restrictions that limit each application's access to user data and the operating system's APIs. This mechanism is designed to protect against incursions by malicious third-party applications and to limit the damage caused by exploitation of a non-malicious application. To implement this, iOS runs each application in a sandbox that restricts its access to the device file system and memory space, and carries a signed manifest that details allowed access to system services such as location services. For applications distributed via its app store, which is the only software installation method allowed on a device with default settings, Apple additionally performs automated and manual code review of third-party applications. Despite these protections, malicious or privacy-violating applications have passed review. So for the newest iOS, which is iOS 14, it includes additional privacy, transparency, and controls features, such as listing privacy relevant permissions in the App Store, allowing for finer-grained access to photos and OS-supported recording indicator, Wi-Fi network identifier obfuscation, and optional approximate location services. Sandboxing for the Android device system utilizes application sandboxing as a mechanism to prevent apps from compromising each other or the OS as a whole. The basic sandboxing mechanism is provided through discretionary access control. which are files that have permission based on their Linux user IDs, which are enforced in the Linux kernel. Each Android app has its own Linux user ID and by default only accesses access to its own files. So any attempted direct access to the files of other apps or the core OS will result in an error. The discretionary access control is enforced by the Linux kernel. Theoretically, bypassing this mechanism would require a kernel to exploit in order to escalate privileges. However, the Android operating system provides many other avenues for inter-application communication, which creates further opportunities for privilege escalation. To enhance the limited security provided by the discretionary access control, Android employs security enhanced Linux, SE Linux, which allows granular control of the privilege granted to an application. For example, in the traditional DAC model, a compromise of root-owned process would be equal to compromising the whole system. With SE Linux, policies are configured so the process is allocated only when the specific privileges are needed to function. This is known as mandatory access control. In this setting, compromise of root-owned process would not necessarily lead to full system compromise, since the kernel would prevent the process from performing actions outside of its capability set. In Android, SE Linux is enforced between the system and individual apps. Apps are confined to the permissions available to their domains, and any violations would result in an error at the kernel level. So the third security feature I'm going to talk about is encryption. Encryption is the transformation of data into secret code. Encryption is also the main effectual method to achieve data security. You must have access to a secret key or a password that will facilitate you to decrypt data which is in an encrypted file. Unencrypted data is called plain text, and encrypted data is called ciphertext. Encryption is significant for mobile operating systems because it provides additional protection against your mobile device. While for Apple encryption, while software protections provide a degree of security for system and application data, these security mechanisms can be bypassed by extrapolating logic vulnerabilities in software or flaws in the device hardware. Apple attempts to address this concern through the use of data encryption. This approach provides Apple devices with two major benefits. First, it ensures that Apple devices' storage can be rapidly erased simply by destroying a single encryption key carried within the device. Second, encryption allows Apple to provide strong file-based access control files and data objects on the device in the event that an attacker bypasses security control operating system. Android encryption uses two forms of user data encryption on Android. A full disk, which is a direct parallel to Linux disk encryption and in its file base, which enables more granular categorizations of encrypted data. File disk encryption is the original encryption mechanism on Android. Introduced in Android 4.4, it is based on the Linux kernel dmcrypt module and a master key to encrypt block devices with AES 128 in CBC mode with ESSIV. The master key, in turn, is encrypted using key derived from the user authentication credential, a numeric password, alphanumeric paraphrase, or pattern. However, because the same key is used for the entire disk partition, Android requires the master encryption key to be available on boot in order to activate core system functionality. Specifically, subsystems such as telephony, alarms, accessibility service remain unavailable until the user unlocks their phone. Once entered, the master key is never evicted from the device memory, as it is needed for all block device operation on the data partition. File-based encryption is a more recent development and provides more granular control than full disk encryption. The underlying mechanism for this encryption is the Linux kernel module and uses AES 256 XTS mode for file data encryption and a CBC mode to encrypt file metadata such as names. File-based encryption segregates files into two categories: credential encrypt, and device encrypt. Credential encrypt data is encrypted using a key derived from the user's passcode and is thus available only after the device is unlocked. Device encrypted data is based only on device-specific secrets and is available during the initial boot and after device unlock. Because of this separation, file-based encryption allows the user to access important functionality prior to user authentication. Credential encrypted data is the default for all application, and device encrypted is reserved for specific system applications. File system metadata is not covered by this mechanism. A different encryption subsystem metadata encryption encrypts this information. The combination of file-based and metadata encryption protects all content on the device as a result. So to conclude, we find that much data in iOS and Android is stored in an encrypted state. The keys are often available in memory. This creates an opportunity for compromised OS kernel to exfiltrate data, as we see in various forensic tools and bypasses. Further, in Android, we find that many widely used outdated versions of Android offer even more limited coverage of encryption, While modern versions offer strong and more granular file-based encryption, older models are regulated to disk encryption. Disk encryption is wholly unprepared for the stronger adversaries we consider in our threat model, where running devices may be seized at any time. In the cloud, both platforms extensively store user data on behalf of the devices. And while there are options for end-to-end encrypted content, such as app developer opt-in backups on Android and certain data categories on iOS, this coverage is limited due to design decisions by Apple and Google. Secure hardware often has compelling security benefits on both mobile platforms, particularly by giving the device a place to store encryption keys without risking their immediate compromise. Secure hardware is the only reliable method of storing encryption keys in the mobile device and protecting them. So here are some recommendations based on the weaknesses that I spoke about earlier. We recommend that you update your software, make sure you have the latest operating system in either device in whichever platform you choose. You want to lock your device, whether that's using facial recognition or KeyPass or whatever biometrics your phone or your mobile device allows for. You're told not to jailbreak or root your devices, and even though jailbreaking is sort of an outdated term, rooting devices is still valid, and it's not recommended because it causes vulnerabilities. And especially for Android, downloading an antivirus from the App Store would increase the security of both your mobile devices, whether it be a phone or a tablet. Adding location tracking is beneficial because if the phone's lost or stolen, you can not only track the phone, but you can also wipe the phone clean. So whoever stole your phone can't use your data for anything. You want to back up your data on the cloud. Both devices offer this. I know Apple's has their own native services that's specifically for cloud services. And you also want to know what you're downloading. You want to know where it came from. With Apple, it's usually screened pretty well in the App Store, but for Android, you definitely want to know where it came from if you're downloading it from an unknown source. And managing your data. You want to control the types of data that's being accessed by your different applications. And finally, we want to use mobile device management software to create an encrypted password protected sandbox for sensitive data. And that's about it. Thank you very much.